we're ready to go. Here you go. Okay, so more on gluconeogenesis today. We had just started talking about the pyruvate carboxylase. Now remember, pyruvate carboxylase is in the mitochondria. The pyruvate, most pyruvate is being created in the cytoplasm, either as a result of glycolysis, where we normally talk about it, or by the metabolism of a number of amino acids you're making pyruvate. So there is transport for pyruvate through the mitochondrial inner membrane. So pyruvate can be transported by a facilitated diffusion carrier. So there is a carrier in the mitochondrial inner membrane for pyruvate. So we get the pyruvate into the mitochondria, and then we need to carboxylate it. And that's where we were on Wednesday before you also rudely distracted me on Friday. Were you looking for video over the weekend?
She told me that you guys had story time on Friday.
Okay. So we talked about the gluconeogenic precursors. We're ready to talk about this reaction. We had talked about the biotin. Okay, so the carboxylase reaction mechanism. This is one of those slides that I put together. It is available, I think, on a... Did anybody get it? No, apparently nobody looked to see if it was there. So, we start with bicarbonate. We start with ATP. We use bicarbonate as the nucleophile, attack the gamma phosphate of ATP, ADP acts as the leaving group, and we make this compound carbonyl phosphate. So we exchange this bond, which is a phosphoanhydride, for this bond, which is a mixed anhydride, right? So in essence, by creating that mixed anhydride, we have activated our carbon dioxide, which was bicarbonate in solution. Then the biotin, one of the nitrogens of biotin, can act as a nucleophile, right? We have this mixed anhydride, we can attack the carbonyl, phosphate can leave as a leaving group, and we end up with our carbon dioxide transferred as a carboxyl group onto our biotin ring. And the biotin then, right, now we've got an amide here, but it is, right, this carbonyl, nitrogen carbonyl, that looks like a urea. That then is the target for a nucleophilic substitution by pyruvate. Pyruvate, carbon next to a carbonyl. The enzyme can deprotonate pyruvate, making the anion. Right, stabilized by being adjacent to the carbonyl. Right, there we go. There's our theme, one of our themes. Right, a lot of chemistry going on adjacent to carbonyls. Pyruvate can act as a nucleophile, attack that electrophilic carbon. The biotin can be protonated and act as a leaving group, and we have carboxylated our pyruvate to make oxaloacetate. Right? That's straightforward. Any questions about that? That make sense?
That's a carbanion LCL. It's really lost for a second.
Where? This? Yeah, that's an unshared pair of electrons in poor resolution. Okay? That make sense? So we take advantage of chemistry next to a carbonyl to create a new bond. And actually that's the way most carboxylase enzymes work. When we deal with other carboxylase enzymes later, biotin is the coenzyme, right? That's what biotin is for. And we take advantage of chemistry next to a carbonyl. So when we carboxylate, we do it next to a carbonyl. Okay? Any questions about that? Yeah, Michelle?
The book, it has like a two-phase reaction mechanism. Is that the same as?
Let's see if I've got that up here. Is this the figure?
Yeah.
Yeah.
I did.
Is that? Yeah, they're showing it, you mean this stage? I think it makes more sense as a direct nucleophilic attack on this, rather than this decomposing to carbon dioxide. Right? Yeah, they're not showing the other basic group. I like my reaction mechanism better. But in the end, it's accomplishing the same thing. Okay? Now, we go back to our figure. We got, what number is that? 12. Right? So we're at oxaloacetate, but we're at oxaloacetate in the mitochondria. Most of gluconeogenesis has to occur outside the mitochondria. So we have to get our oxaloacetate out of the mitochondria. There's a problem. There's no carrier for oxaloacetate in the mitochondrial inner membrane. And since the mitochondrial inner membrane only lets things in that are either nonpolar or that it has specific carriers for, that's a problem. So what we have to do is use the citric acid cycle enzyme malate dehydrogenase. With malate dehydrogenase, right, we're doing gluconeogenesis at a time when the liver is well fed, right? There's lots of NADH around. Where is the liver getting the NADH to sort of push gluconeogenesis through? Well, what does the liver prefer to use as an energy source? Robert? Okay, but where is it getting the carbon for the citric acid cycle? No, we're using our pyruvate for gluconeogenesis. So where are we getting starting material to enter the citric acid cycle?
Lipids and amino acids?
Lipids and amino acids primarily. So let's go with fatty acid metabolism. It gets back to my climbing the stairs example, right? You climb the stairs, you get to the top of the stairs in this building, you feel fine. But climbing the stairs is an anaerobic activity. So your muscles make lactate. They export that lactate to your liver. Your liver makes it into pyruvate, wants to do gluconeogenesis with it because the muscles have been working, sends it into the mitochondria. The liver uses fatty acids to generate NADH. But some of that NADH is going to go to the electron transport chain. You start using oxygen because your liver is using oxygen to drive this, to make both ATP, which we're going to need, and NADH. So halfway down the hallway, you realize you're breathing hard. You felt perfectly fine when you got to the top of the stairs. It's not till you get about to that window halfway down the hallway that you start breathing hard, because that's when your liver is trying to catch up. And it's using fatty acid oxidation to drive this process. Okay? Does that make sense? So, as the old guy in the room, I use this as my justification. I walk up the stairs, I get halfway down the hall, I'm huffing and puffing. What do I tell myself? I'm not out of shape, it's just my liver catching up. Right? So, the NADH is coming from fatty acid oxidation. So fatty acid oxidation, high NADH under those conditions in the chondrion of the liver, pushes this equilibrium toward malate. There is a carrier for malate in the mitochondrial inner membrane. So malate can escape the mitochondrion and get into the cytoplasm. Then once malate is in the cytoplasm, NAD in the cytoplasm is used to make NADH to reoxidize the malate to oxaloacetate. And so in essence, we're bringing these 4 carbons out, right? Oxaloacetate is 4 carbons, malate is 4 carbons, malate is 4 carbons, oxaloacetate is 4 carbons. So we're bringing the oxaloacetate out, and we're bringing with it 2 electrons from the mitochondrion. That creates the high NADH in the cytoplasm that's going to drive this step when we get up here. It's going to push the equilibrium of this step that way. So by doing it this way, we accomplish not only moving the carbons, but also moving the equivalent of 2 electrons that will help change the equilibrium of this step and push it more toward the gluconeogenesis direction instead of the glycolysis direction. Does that make sense? You see the way that works together? Now, the other choice, especially if we're doing, if we're not shuttling NADH out for some reason, oxaloacetate can receive an amino group from glutamate to make alpha-ketoglutarate. Right? So oxaloacetate can become aspartate. Aspartate can be transferred out of the mitochondrion. You can reverse that. Alpha-ketoglutarate in the cytoplasm can be made into glutamate. And you can shuttle the 4 carbons out without shuttling the reducing equivalents if metabolic conditions are slightly different. That's what this cycle is. Okay? Yeah, Robbie?
So why did pyruvate go into the mitochondria? Was that
Well,
because they get the NADH?
Well, right. Well, because we've got